Hi, I'm Aryan Chaudhary. This is my physics lab for oscillations. So, the table of contents in this lab, I'll be going over five main things. First, the introduction and the fundamental principles. Second, the experiment, then computation model, and then finally, results, conclusion, and error analysis. So the objective in this experiment, I'll analyze the motion of the spring mass system, and then I'll create a computational model which tries to predict that motion. Then I'll plot both the predicted and the annual motion and compare both of them. The key ideas: Newton's second law, rate of change of momentum is proportional to the net force on the system, and the energy principle. So, the system in this case is the mass, spring, and the earth, and the surroundings is nothing. So, the fundamental principles are as follows: the gravitational potential energy is mg delta y, the spring potential energy is half into ks, which is the extension squared, then the kinetic energy is half into mv squared. The energy principle states that delta E is of in a system should is equal to the work done by surroundings plus the energy changes. And since the surrounding here is nothing, delta E should be zero. Newton's second law includes the position update and the velocity update formulas that we'll use in the iterations. So this is me tracking the motion. So the values for the motion in x-axis and the y-axis was stored in an Excel file and then imported in a CSV format for the computation code. Then the computational model, the initial conditions are as follows. So the values for ball M, the ball mass, the ball's position, and the ball's velocity were put as shown here. And then for the initial spring conditions, the following formulas were used. The time period for 3 oscillations of 4.571 seconds. So the time period was was calculated as 1.5237 seconds. And then the spring constant was calculated using the formula 4 pi square into m by period squared, so which came out to be 6.83. Finding out the relaxed spring length L0, since we knew the L, the magnitude of L in the beginning, which was 0.7 meters, we using the formula Fs is equal to Fg by gravity, we found out the relaxed length of the spring. And finally, we use the formulas for the kinetic energy, spring potential energy, and the gravitational potential energy, and the total energy, which as discussed before in the fundamental principles. Then for the computational model, first we define the initial values for kinetic energy, gravitational potential energy, and the spring potential energy as shown. Then we input the formulas for the gravitation and the spring force as shown in lines 114 and 117. Next, we use the position and velocity update formulas, which is part of the Newton's second law, which was also discussed in the previous slides. Then next, we'll again calculate the final energies and the energy changes for K, UG, and US and E at each iteration based on the new ball position values. So the results were as follows. The following are the graphs for the predicted motion and the actual motion in both the x direction and the y direction. We can see the computational model mimics the actual motion well. And error analysis, there were a few discrepancies between the predicted motion and the actual values. This could be because of the drag force, which the model did not account for, which is the air resistance that the ball feels, and the human error. Since the ball was tracked manually, this would still the data collection is still subject to human error. Then the conclusion, what does it mean? For the model system, is the energy principle satisfied? I believe yes, it satisfies the energy principle. As we can see from the graph, the delta E remains constant at 0, and the kinetic energy and the gravitational potential energy mirror each other, which are mirror images of each other. Therefore I believe it satisfies the energy principle. The second question, I had to make two estimates of the oscillation period. So from the x values, I found out the period to be 1.6463 seconds, and from the y values, it came out to be 1.5753 seconds. So we can see from the above calculations that the period for x and y axis, period for the oscillation in x and y direction is different. Thank you.